This is the lecture on amino acids. And all right, so I'm going to start with a general overview of the amino acids and give little details on them each. I know probably most of you, or maybe not, I mean, there's no shame if you haven't, but maybe most of you probably have gone over them since it's like the one thing you can memorize and you want to get it over with as soon as possible. What I found is that most companies do a good job at this, at describing amino acids. So you really have like anywhere you can go to. So the first amino acid is glycine, and you have to know the single letter node designations for them, because a lot of the times when you do passages on the bio sections, they will designate, like if they're doing a genetics passage or they're doing a biotechnology passage, they will designate amino acids by their single letter designation so as to get you, so you have to memorize them. So I'm putting them on here. I mean, they're probably in your book. As I said, I'm only generally reviewing them before I go over titration curves. So the first one's glycine, and it is well known to be the only amino acid that what was it? It's generally known as the only amino acid that is achiral, or is not chiral, because remember, guys, what chiral carbon is when, well, this is not chiral, so what am I doing? Chiral carbon is just like in this case, you have 4 different groups, right? And here would be a hydrogen. So it'd be an alpha carbon because it's chiral. And this is an example. Each case is different because the side chain is different. But in glycine's case, because the side chain is a hydrogen, and then there's another hydrogen here, it can't be chiral. So in this case, it's achiral, and it's simple enough. And it's one of those amino acids that can easily fit into secondary structures. Okay, next is alanine, and that's also a simple one. It's just CH3. Its designation is A, and don't confuse this with arginine. Arginine's an R. I made that mistake, I think, my first video. Valine is pretty simple. It's just the same thing as it's just 2 carbons and then a branched carbon, so a propanol group. For leucine and isoleucine, don't confuse the two. A lot of people, especially me, thought that this is leucine because it was in the first position, and then this was isoleucine because in the last position. It's not. So leucine has the extra carbon on the second to last carbon, and then on isoleucine is on the first carbon away on the side chain. So know the difference between the two, because I know a lot of people confuse them, and I was one of those people. Methionine. Methionine is the only oh, I also forgot to mention. So what I want to say about amino acids, I actually forgot. I can't believe I didn't start out with this. When I want to start with amino acids, they divide into specific. I think the best way to memorize them is think about them is to memorize them in succinct groups. So the first group would be non-polar amino acids. So this is the first group I'm covering, right? And there are 5 is it 5 or 7? 7. It's 7 amino acids in this non-polar, non-aromatic amino acids. I should write non-aromatic. So think of these as non-aromatic. Non-polar, non-aromatic. And what does non-polar mean? Well, it generally means hydrophobic. So these are hydrophobic. And what does that mean? It means that in most cases, it would not be on the outer part of a membrane. It would probably be the inside because, like, it's non-polar. So what was I saying? All right. So methionine is the only sulfur group that is the only sulfur group side chain, or the only side chain with a sulfur group that is non-polar. Because it's not polar because it has a CH group attached to it, and that CH3 group attached to it. And because the CH3 is bound to the sulfur, it's drawing away its electronegativity. Because sulfur has a large amount of electronegativity, but so if it were like in cysteines, which I'll discuss in a minute, cysteine, you would have like a large amount of electronegativity here, so it would be polar. But in this case, because there's a CH3, it's stealing away that. It's like, I don't know, this is a really good. I remember my pharmacology professor brought this up. It's a union, so it's taking away all of your energy. So it's like he said it was like a marriage, and I thought that was comical. So, which I mean, not many of you might find that funny, but I don't know. So it's like a union. So the CH3 is stealing all of the way the energy from the sulfur, so it's making it non-polar. So think of it like that: methionine, and proline is one of these groups. But what's unique about it is that it's this amino group. It's attached to its side chain. So you have to memorize the structure, of course. And rather, it's not really an amino acid. It's an amino acid. I mean, I wrote it down, but I'm going to write it down anyway. I can't spell. Oh my god. And what do I mean by amino acid? Well, because it's an amine group. Because and you have to know the difference between amine group, and inamine group. So an amine group generally looks like this. It has the double bond to the N, and it's attached to another group. It could be an H. This could be an H, but like that's generally the structure. You find this kind of and then enamine is rather this kind of group. So you could see that the difference is, I mean, there's not really much to say. You just have to memorize how they look like and how to recognize them. So in this case, an amine is double bonded N to C, and then this is an enamine, so you transfer the double bond, and then it's attached to it's a double bond here. So it's like, and then instead of that, you have so yeah, you transfer it, yeah. So it's generally not that bad. And proline is unique because it's one of those amino acids utilized. You find this in collagen a lot of the time, and it's mostly deals with secondary structure explanations. So proline is utilized in stuff like cartilage, because in cartilage you have a sequence of glycine, another amino acid, and proline, and it introduces rigidity. And it introduces limitations in the secondary structure. It might not be collagen, it might be something else. But in a sense, proline leaves not much room for any other amino acid but glycine to be able to fit in, because the side chain is so small. So proline introduces, in a sense, is the amino acid that introduces rigidity to a secondary structure. So that's essentially what it means. Do you guys have any questions regarding these amino acids? I know I'm going fast, but it's not that complicated. It's just a theory. I'm just noting like extra stuff you should know about these amino acids before I discuss how do you manipulate them. So you understand these ones so far? No glaring questions? Let's take that as a yes. All right, so the second group you should know is the non-polar aromatic amino acids. These are still hydrophobic, so that still applies. So I'll write that down right here. And excuse me my terrible writing on this thing. I'm writing on a mouse, and if I had a trackpad it'd be different, but nope, I'm working on a mouse, so you'll have to bear with my handwriting. So it's hydrophobic, and it's aromatic. And there are only 3 amino acids here, so it's not that difficult to memorize. So phenylalanine is not that complicated. It's just a benzyl group, benzyl, you know, because it has the CH2, a benzyl group. There's my Tilburg handwriting again. I like making giant loops with the Y's. And it's easy, phenylalanine. It's just like it's a simple aromatic structure. It's like you have the CH, the alanine, and then you just attach a aromatic 6-membered ring. Just like that. Okay. So tyrosine. So this little thing right here is when it's when I'm going to talk about the titration curves, because there are 7 amino acids, and out of all the 21 amino acids that have a third pKa inside from their side chains, which cause there to be 3 loops in the titration curve, and tyrosine is one of them. And I'll get to the specifics, but when you see this circle right here is regarding that. So tyrosine is basically phenylalanine with an OH. It's not that complicated, it's just OH. And the way you can remember the single letter designation, Ty, Y. And tryptophan is a lot harder to memorize, but you still have to memorize it. So it's the, and it's, you can remember the single word designations. It's like the last letters in the last few letters in the alphabet, Y and W are aromatic. You can remember it like that, because majority of the case, like a lot of the letters in the alphabet are utilized for the obvious amino acids, and then for like the ones that are left over, they just put those single word designations in, and you'll kind of see this when I talk about the charged amino acids. So when you think of the end of the alphabet, think of like the aromatic nonpolar amino acids. So, and also aromatic amino acids, they're hydrophobic because they're nonpolar. Okay, now for polar amino acids, there are 5 of them. And what does polar mean? Well, polar means that they're hydrophilic. I'm gonna erase this because I don't need it anymore. They're hydrophilic. And hydrophilic, as I said, is the opposite of hydrophobic, means it loves water. So, and it can deal with being in aqueous environments. What else am I missing? It's on the outer part of the membrane most of the time. So these are amino acids you would find most of the time in the outer membrane. And then, yeah. And these are the non-charged version. These are non-charged amino acids, polar amino acids, because I'll get to it in a later when there are other polar amino acids that are charged, that have charged side chains rather. So serine is pretty simple. It's just you have an alanine and you attach OH to it. And then threonine is also not that complicated, just switches the position of the OH. These are 2 kind of important in cellular signaling, because a lot of the times that this OH, they kind of go, these groups go to, and tyrosine as well, is also a group manipulated in cellular signaling, whereas you can phosphorylate this and turn to an OP to move around a high energy phosphate. So think of it like tyrosine, serine, and threonine, because they have that high energy OH group, and which can undergo phosphorylation. They're utilized in cellular signaling, especially with regards to cytokines, and it's getting on my memory right now, but it'll come to me. Cysteine, remember, I'm going to go over this reaction again because apparently in the last video I misdrew the structure. I put an extra CH2 in the structure. It's actually the cysteine, it's only it's only alanine, and then you attach a C as an SH. So it's not 2 CH2s, it's only 1 CH2. And the reaction of making a disulfide bond with regards to cysteine is very important. I'll review it again because I think it's important. It's really important for you guys to memorize. So you have 2 cysteines. So that's oxidation. And that's a really badly written one, but I'll just keep going because you guys have better. And then the 2 hydrogens and 2 electrons. And then for the reverse would be reduction, because you would take back those electrons and hydrogens in order to break the bond and give the H's to the 2. And remember, in biotechnology, you have reducing and non-reducing conditions when you're doing SDS page. Gel electrophoresis. Excuse me for my bad handwriting. And then this is a disulfide bond formation and destruction. And a disulfide bond is an example of a covalent bond. It's a very strong bond. That's why when you go through normal denaturation, it won't destroy a covalent bond or a disulfide bond. That's why you have to go through, when you do SDS page, you have to undergo reducing conditions in order to go through the reduction. So that's essentially cysteine. And cysteine is polar because of you don't have a CH3 stealing the energy, so the electronegativity is like large. And cysteine is also the other amino acid that has a third curve and a titration curve, which I'll discuss later. The other two, these are pretty easy to remember, or the structure to remember, because they're basically the same as 2 other amino acids, but they have NH2s attached instead. So this is asparagine and glutamine, and this can sometimes people forget these the most because they have nothing to do with one another. So, like I said, this is how I pictured it in my brain, and I don't know if it'll work for you guys as well. But for me, when I was doing this, when I was memorizing amino acids, I thought to myself, the other letters kind of fit in with their normal spelling in the alphabet. So the leftover letters, I'll just like think of it as being associated with those amino acids. So with asparagine and asparagine, and it's the 3-letter designation, ASN, N. So, and then what's the next in the alphabet for the next letter that isn't used? Q, glutamine. So that's how I saw it. Asparagine and glutamine are close, but like glutamine has one more CH2. It's basically that. And always remember, I draw my amino acids like this because it's how they did it in Kaplan, and that's how I learned it. I mean, you can draw it in the horizontal way if you want. It's just, this was always easier for me because it made it obvious of the side chain what it was, because it emphasized on that. So, yeah, I think, what else did I have in mind? Oh yeah, this is generally the same structure as glutamate and aspartate, which I'll discuss in a second, except there's an NH2. And these are polar, not charged. And do you guys know, wait, no, is it that? Do you guys know what kind of bond or what kind of group this is? I'm testing you now, so it's not a rhetorical question. Do you know what kind of bond this is? Or rather, what kind of group this is in organic chemistry? Functional group? Think really hard. Yeah, oh no, no. And an amine is something else. Amine is this or this. You're close though. Does anyone have any more guesses? Okay. Give me a sec. This is an example. No, that's not an amine. An amine is different. It's an amide. An amide. An amide is basically a NH group that's attached to. So, if you guys remember from your organic chemistry, or no, that's not right. So it's basically an amine group, but it's attached to a carbon at C double bond O. So an example, so in a lot of cases, carbonyls can be changed into amines by certain reactions. But so you can, in organic chemistry, you can take a carbonyl group or like a this and react it with, I believe it's this, I could be wrong, and then have and kick this off and kick this off. I might be right. I might be wrong about the reactant here, but there are a bunch of reactions where you can change this group into different derivatives, and an amide group is a derivative. I think it's actually an amine that it reacts to. Give me a second. I have to double check this. Give me a minute. It's carboxylic acid when it reacts to it. I was wrong. It's an amine. So you react with the amine. That's how you make an amide, actually. I mean an amine. But to change a carboxylic acid into an amide, you take and then you react it with, and you get. So that's how you do it. So if that's to your general knowledge. So you should know your functional groups. I'm not kidding, you really do, because I know for a fact on the what's it called, on the on the MCAT they do have a lot of organic chemistry in it in the chem section, or at least it did on mine. And I think it's best if you know your functional groups. You need to know what an amine is. You need to know what an amine is. You need to know what amine is, or an amide. You need to know what an anhydride is. You need to know what, and of course, carboxylic acid. I'm missing one. An ester, an ether, sulfonyl, I believe, as well. You can look up any general list of functional groups and find them, but you do need to memorize them. Okay, what else am I doing? Okay, now we're gonna cover okay, do you guys understand that concept though? Like, does that all make sense so far before I move on? Okay, yes, is that, okay, I'll take that as you understood it. I want to make sure you guys understand it before but I'll just take this as a yes. So next is let me move down. These polar negatively charged amino acids. These are hydrophilic, and they're negatively charged. So I call this aspartame and glutamate. Another word this is the name you would refer to it if it had if it had this structure. Another name you could give it is so I'll put this back the way it was. Another name you could give it for these two is aspartic acid. And glutamic acid. They're generally the same structures as asparagine and glutamine, except they have carboxyl groups instead of amide groups. Positively charged, there are 3 of them. They're the same hydrophilic, and they have positively charged side chains. They're a little harder to remember, in my opinion, but as long as, and lysine, for example, is a K. Arginine, R. Don't confuse it with alanine. Histidine, don't confuse it with histamine. Histamine is something else with the immune system. Histidine. And that structure is pretty hard too. The reason these are circled is that some of these structures, it's hard to tell which one's going to get protonated when it goes through the titration curve. With arginine, it's this group, this amine group, or amine group. Or no, this is not an amine group. It's attached to an N, so it's not an amine group. Never mind. Ignore what I just said. This is just this group. This NH here is what gets protonated if it goes through the titration curve, and here is the N that gets protonated when it goes through a titration curve. So glycine, it's just generally amine right here. Here it's pretty complicated structure, but you just have to memorize it. It's just a general concept of memorization. So does that all make sense? And these are positively charged. So, and I'll get into those in a second, but the list of amino acids makes sense in a sense, because I'm going to move on to like proteins and like general structure, but I want to make sure that you guys like know, like, that you have no questions regarding amino acids specifically, other than titrations, of course. No? Okay, well then I'll move on. So this is a PowerPoint that my friend made, and a lot of this covers what I said, but some of it is pretty helpful. Amino acids are amphoteric, meaning that they can donate or accept protons. You could be acidic or basic, which acidic is the negatively charged amino acids. Positively charged amino acids are basic, and then there's neutral. And they have different structures when they go through a titration curve a lot of the time. They have a cation, so positively charged can't form a zwitterion, which is when it's neutral. And an anion form, which is when it's negatively charged. So zwitterion is when the charge is 0. It's when you have the pi value. That's what it refers to. No, I already know this. I already talked about this. A lot of MCAT books say that you need to know these 2 reactions because they're different ways of understanding how amino acids are made. I don't remember seeing them in any tests that I took, but you should probably know the general idea of how, what the mechanism is, and I'm not gonna go into the mechanism because, I mean, it's something like the double bondo, it donates its electron to the I'm sorry, no. It donates the electron to the hydrogen gets bound to it, it gets protonated. This is not hydrolysis, sorry. This is, a hydrogen version of donating the electron. So it forms a bond with the hydrogen, then the NH3 comes in, gets its lone pair, comes in, kicks off the OH group, and the OH group is now on its own, or rather the OH group no longer has the double bond. So there are 3 groups or 4 groups attached to it. Now the lone pair gets donated to the amide, and then it kicks off a hydrogen, and then this group comes back in and gets it. So basically this whole reaction is a way of getting rid of this C double bond O and making it into water and replacing it with this group. So eventually this group can get rid of the triple bond and make an amino and a peptide bond, which makes up a amino acid. The Gabriel synthesis, that's a Strecker synthesis, by the way. This is all look, I think in the majority of MCAT books these two are in, so if you need more specification on them, they have it there. I don't know if it's really required. You just need to know the general mechanics of what makes up a peptide bond or an amino acid bond. Yeah, I'm not going to go into that. And these are just written out structures. You already know this. Reactions you can make a peptide bond essentially by going through condensation. So you put in water, and then you make a bond, and then you break a bond by I'm sorry, no, what am I saying? That's mixed up. No, you make a bond, you take away water from it, and water is not in there. To break a bond, you put in water. So to make bond, you do condensation. So away with you water. To break bond, loves water. And hydrolysis kind of just says this. So hydrolysis is breaking of a bond majority of the time. So, and hydrolysis means putting in water. So you put in water to break a bond. And peptide bond is made through condensation when you take away water. And I already discussed the cysteine thing. Yeah, the disulfide bridge. That's just another way of showing it. I don't need to know that. So now I'll talk about proteins, but no, actually I'll talk about proteins after I talk about the titration curve, because that's actually more pressing. So, do you guys have any questions before I talk about titrations? No? Okay, all right, I'll just move on. So, titration of amino acids. So, it's not that complicated, but the problem is that not many people explain it well enough. I was lucky because my Chem 101 professor had us do titration curves for amino acids in our first semester, considering most of us were pre-med. So, I mean, I got lucky, but I don't think a lot of Chem 101 classes teach you titration curves with regards to amino acids, but I'm going to show you anyways. So, titration of amino acids are basically another example of a titration between a weak acid and a strong base. And a weak acid and strong base titration curve generally looks like this. So I'm going to demonstrate this with a neutral amino acid first to make it simple so that I'm not confusing you, to give you the general makeup of how these things work. So glycine, as you know, has, in glycine, there are two groups that have a P. The whole point of a titration group, you have two areas that have a pKa. So in the first case, the first pKa is around a 2.34, and the second pKa is around a 9.6. The pKa's are on the carboxyl group and the amino group. So the carboxyl group and all amino acids, you don't have to memorize these values, but just generally think the carboxyl group and almost every, in majority of amino acids, are gonna be at around a range, are gonna be around a pH or pKa of 2.5. Here's a 2.3, which is close, but like all of them, you don't have to memorize the specific pKa because they're all different. But generally, most pKa's of the carboxyl group is a 2.5, and for the amino group, most of the time the pKa is around a 9.5. Here it's a 9.6. Like I said, it's different in every case, but it generally follows that. So just memorize from now on, like, those two groups of the main amino acid. The side chain is another story, but in this case, in every sense, the amino group is around a 9.5, and the carboxyl group is a 2.5. And what does it mean when I say pKa? Now I'm going to discuss that in a second. So here, when we're in this case with this amino acid, we have a solution of a weak. The amino acid is a weak acid, and you're giving it strong base. So at this point, when you add strong base, you're adding strong acid. You're taking away the proton from from the carboxyl group. So as slowly you put more hydroxyl, the OHs, you take all these OHs that keep going in keep stealing protons. They keep stealing protons, keep stealing protons, keep stealing protons until it reaches the pKa. And the pKa generally means that the amount of acid, a weak acid, and the amount of conjugate base are equal. Now, if we're going to go to a general review with general chemistry, what does that mean? In general chemistry, remember when you have a acid you have a weak acid and a strong base, right? You have the acid, and then when you take away the proton, it becomes a conjugate base. In this case, with the pKa, the amount of acid and conjugate base will be equal, meaning that the amount of weak acid got its protons stolen, and still there are half left over that have not had their protons stolen. So generally, every time there's this position on a titration curve, you know the pKa is right there, and you know that the amount of acid equals the amount of base. I had it labeled differently because you have another pKa, but like it means the same thing. Like this means the same thing. It's just because you have another part of the pKa getting deprotonated. I just wrote it out like this. So in this case, in this one is 2.34. The amount of A equals HA. This is the acid in this reaction going on. This is the acid, and this is the conjugate base. And the acid's hydrogen here got its stolen by the OH group, and it became CH2. It became H2O, and this was the conjugate base that resulted. And then as you keep going high on the titration curve, you have more hydronium, the more OH group, more base, more base, more base, more base, until you reach the equivalence point. And the equivalence point is when the charge is, this is when this Zwitter ion is appear, and the charge of everything is 0. So that means that all of the whole solution has now become the conjugate base. So no longer is it half, now it's all conjugate base. So now you can move on to the next pKa. So now you keep adding the OH, you keep adding OH, you keep adding OH, you keep adding OH, it's at this point, after the equivalence point, the conjugate base now becomes the acid. So it's switched because you keep adding, you have another group, right? So, like it's right here, this is what I'm saying. You keep adding OH, you keep adding OH, you keep adding OH until you get a conjugate base. So the conjugate base is this. So then at this point, the amount of acid equals the amount of base, the second pKa, which is at the ammonium ion. So now the proton is being stolen from the amino group. So the two pKa's are generally telling you like what section of the amino acid is getting its proton stolen away from the strong base. So, and after you pass the pKa, it goes, more protons are getting stolen, more protons are getting stolen, until finally the amino group has its proton stolen. So now it's negatively charged, the amino acid, because the protons were taken away. So, and I'll show you on glycine structure how that'll work and see. And when pKa, since pKa equals when the acid equals the conjugate base, it refers to the Henderson-Hasselbalch. Did you guys remember in general chemistry the Henderson-Hasselbalch? Well, generally it works like this. Math is so fun. You'll see in a second. So generally when you have, you have pH equals pKa plus the log of the concentration of conjugate base over the concentration of the acid, right? So generally you have the pKa, so here will be like 2.34, right? And at the pKa, since we reached the pKa, we know that this will equal this. So that will equal to a ratio of 1. And log of 1 equals 0. So then you would have 2.34 plus 0 equals the pH. So the pH would be the pKa. So that is how the equation, that's how math works essentially. So the math works essentially. And it's the same thing when you get to the amino group. So after you reach the equivalence point, you do the same equation so it'd be pH equals 9.6 plus the log of the conjugate base over the acid. And the same thing, log of 1 equals 0, so the pH at the pKa2 would be 9.6. So when it reaches pKa, you know that the total amount of this equals this. So the ammonium ion has been targeted. And so you can see this in the structure. So at 2.34, so at the beginning of the reaction, before any of the base was added, you had this structure, right? This had its hydrogen, this had its hydrogen, right? Now, as you add more OH, you add more OH, you add more OH, and the pKa1 is the reaction. These are totally reversible, but you add more OH, you add more OH, and then you get to the Zwitter ion form. So as each amino acid in the solution gets its proton stolen, it'll reach this structure, the Zwitter ion, which is 0 because you see plus minus 1 equals 0. So the first group, since it's the first group that gets its proton stolen, is this group because the pH, we reached the pH already, is 2.34. We haven't gotten to the pKa here yet because we haven't reached the pH yet. So its proton doesn't get stolen yet. Its gates are closed. But these got their protons easily stolen because they have a low pKa. So so then you add more OH, you add more OH until the pH reaches a 9.6, which is the pKa of this group. So the gates are open, so you can steal the proton away, and now it's a -1. So this is how it generally works. Like, as you add more OH, you steal a proton from a group depending on what the pKa value is. Does that make sense in general? Like the whole titration curve? Which one do you want me to repeat? Like this reaction right here? Okay. So remember how in the beginning, so this structure is right here in the reaction, right here. So we had added no OH, right? Or NaOH. So we add more OH, and the pH is going higher. So we were at a pH of, for example, a pH of 0.5, right? We go up, we add more, it gets to 1, it gets to 2, and then finally when it gets to 2.34, the gates are open to this group because the pKa is at 2.34. So then you can steal the OHs can steal the hydrogen. So then the next structure at each amino acid, when it reaches the 2.34, it'll get its proton stolen. So then you have this structure, the zwitterion, a charge of 0. And then you raise the pH, you raise the pH, you raise the pH, so now you can get to a pH of 3. It's still the gate, you can't steal this yet. Get pH of 4, you can't steal this yet. Get pH of 5, can't steal this yet. 6, 7, 8, 9, and then a 9.6. So now you can steal the proton. So then, because it reaches at the pKa. So now the proton gets stolen, and then the charge overall becomes a -1 because you got a negative charge and there's no positive charge to counteract it. So at this point in the reaction, you've gotten here. You've gotten past it. This is one amino acid, but and so when you have a general solution, the whole titration refers to the whole solution. So then in this case, you get to the second equivalence point, and the second equivalence point would be all the amino acids in the solution have gotten to this structure. But each amino acid has to go through this whole reaction, right? So the titration refers to a solution of amino acids, and this gives you an example of what each amino acid goes through, basically. So each amino acid starts in this structure, and as with each pKa change, each pKa means which section of the amino acid will have its proton stolen, essentially. So that is the general makeup. And it gets more complicated when we talk about side chains, but I want you to understand how the neutral amino acids work before I get to the side chain. So does that work? Does that make sense, essentially? Is anything confusing? Okay, good. No, you can also have another titration where it gets more complicated, but most of the time because amino acids because they have the protons attached to it, most titration curves they do refer to a strong base because a strong base will want to steal the protons more. But there are other titration curve types. I have to look up the specific ones again. There's strong acid, strong base. There's this titration curve is an example of a weak acid, strong base. You can have a strong acid, strong base. You can have a weak base, strong acid. And weak base, strong acid would be this is a really bad drawing. Weak acid, strong base would be generally the opposite, so it would be like this. So it's PKB or PKB, yeah. So then it'll be you add more CH3, and each group. So you would start out, you probably do the reverse. So it'd be this. The whole thing would start out with this. And then you go through the first pKa or pKb, I'm not sure, but the first pKa for the amino group. What am I saying? Yeah, pKa. And then you would do the first group that gets its proton back because you're adding hydronium ions because you reach the pKa will be CH3, and you get to reach the Zwitter ion, and then you reach the pKa for this group. So then you reached at the 2.3. So then eventually it'll get to R. Oh my god, I'm sorry, my handwriting is not that great. I'm like rushing it. So it got protonated because you added more hydronium ions and their protons are being returned. So you can do the reverse, of course, but like, I don't know, I've been mostly tested on when you add when you add OH groups. So you can do the reverse. It's just the same thing, but gone backwards. You see what I'm saying? So it'd be like taking this and going backwards, right? And the curve would generally look like this instead. I'm badly drawn. I can do this better. What am I doing? So pKa is like 2.5, I mean 2.3 in this case. And then I think a strong acid, strong base is a lot more, obvious, I think maybe, but I don't know. So you would add strong base to a strong acid. I think it mostly looks like this. It's a lot more, but amino acids aren't strong acids, and so that's different. And I think the titration curve for a weak acid and weak base is like that, and it's a lot weaker. But like general, you can look them up like the official. But if you want to do the reverse and add hydronium ions, it's just the reverse of this reaction. You go this instead of going this way, you would start here and go generally that way instead. Does that make sense? It generally depends on if you're adding OH or a titration is basically like you've probably done them in lab. It's just you're adding a base or acid to a solution, right? You're going through a reaction. So it's just like as long as you understand the mechanisms of like you either giving a proton or taking a proton. That's essentially the main concept. It's just like made more complex. Okay, good. So I'm going to talk about the side chains because that's going to make it more confusing. I'm sorry, it will. But so I'm going to give an example of lysine because lysine is probably one of the more simpler structures. Lysine is one of those positively charged amino acids. So in this case, we have something different going on. So it's the same. You had OHs, and the first group that gets attacked and gets its proton stolen is the hydroxyl group. So I have it drawn on the bottom, but I think it'll be easier if I just do it here. So I think that's easier. I have to remember 1, 2, 3, 4. Now, this is important. So everything is protonated. This is the beginning. We're at a low pH. So generally, like, for example, this would be a pH of like 1.5, right? So we know this. So the side group, remember, this is positively charged as side chain. So we know that this will be positive. The proton will be here. So in the beginning, when there's no OH groups, this is a charge of +2, right? So then we keep adding OHs, and we reach a pKa. So so at this point, half of the solution will be acid in this structure, and half of the solution will be in this structure. So it got its proton stolen. This still has its proton because its pKa hasn't been reached. Oh god. Excuse me for my bad handwriting. That's an N. I'll erase that, put an N. That's an N. So half at this point at the pKa, half of the amino acids in the solution are in this structure and half of them are in this structure. The conjugate base, right? So now we have a charge of +1 because these two cancel each other out, and the only charge this is positive charge. So now, and then here at this point, you know, I don't think I should have put it there. I think I'll just move this here. And so here, this is the equivalence point, and that's generally where the pi is. And this is, no, it's not the pi, the zwitterion hasn't been reached. What am I saying? Pi, remember, pi only has to do with the zwitterion. So whatever structure the zwitterion is in, that'll be where the pi is. And this is not the zwitterion, of course, because this is a +1. So I caught myself. So now the whole, at this point, all the solution is in this form, right? So now we want to get to the second pKa. So we'll take away more protons, get higher, until the pKa2 is reached, which is around a 9. So the next position to get its proton stolen is the amino group, right? So it's gonna be like this. Oh my god, what do my N's look like W's? So now this is an actual zwitterion because these two cancel each other out, and this isn't charged anymore because it got its proton taken away. So this is a 0. This is the zwitterion. So here would be the pi. Because the whole solution has, after you reach this, the second equivalence point, all the solution and all the amino acids in solution have become this structure. At the pKa, half of the solution is in this structure, half of the solution is in this structure. Because as I said, it's just explained here's the Hasselbalch. But now you still have to deal with this guy because more OHs are coming in, and OHs still want the hydrogen. They can't stop when they know there's more hydrogen stored away. They're gonna keep trying to get more of it. So the pH keeps going up and up and up and up and up and up and up until the gateway is finally open for that side chain. So then you go through another pKa, which is in this case at 10.5. So then and now you have a charge of -1. So they could not escape the wrath of the OHs. So now finally you've gone to the final. And then when you reach the third equivalence point, all the solution would have reached this structure. And at this point, this pKa would have reached halfway of this and halfway this. So basically it's just a step-by-step like way of showing like the reaction of how the structure will change. And that's an example of how the side chain would work. So essentially, there are 7 amino acids that have this kind of tendency. It'll be the charged amino acids, so lysine, arginine, histidine, aspartate, and glutamate, and then 2 more. It'll be the tyrosine. The group that'll get the tyrosine, and that group will probably be the OH attached to the aromatic group. And then the next one would be cysteine, and cysteine is the sulfur. So you take away the hydrogen from the sulfur. Cysteine has around a pKa of 10, I believe. You'll have to double check. Tyrosine has a pKa around 6, but or no, it has a 10.5, I believe. but you have to double check. Glutamate and aspartate, they both have pKa's around 4.5 because they have, it's the second carboxyl group, so it has to be a low pH. So then, like in a titration curve, it would be the first one to get its first group to get its proton stolen would be the OH's, the OH, the normal like OH group from like what I've shown you, and then the second one would be the OH on the side chain because its pKa is 4, and then the third group would be the amino group part of the original structure. So that would be a little bit different. It's just because the pKa is lower. And then for the basic amino acids, from what I recall, arginine has a pKa, the side chain has a pKa of 12.5, and then I think I wrote it down on you can look them up. I mean, there are only 7 amino acids that do this. As I said, tyrosine, cysteine, the 3 basic ones, histidine, what was it, arginine and lysine, and the 2 negatively charged ones, aspartate and glutamate. And then here's another example of how, like, this is basically the overall what I showed you. You start with lysine, positively charged, all happy, has all of its hydrogens. The OHs come in after the pKa is reached. The OHs steal away from this group, right? And then as more OHs come in, they steal from this group. No, but Zwitter ion is reached, and it's not satisfied because they know that the side chain is hiding away hydrogens, so it keeps going until the pKa for the side chain is reached, until all of its hydrogens or positively charged groups have had their hydrogen stolen. And in this case, the pKa would be here. So, do the titration curves make sense? I don't think I'm missing anything, am I? No, I don't think so. Do titration curves generally make sense, though? Is there anything that's confusing you guys? No? Okay, all right. So I'll just do a general overview of proteins. I don't want to go into I mean, I kind of covered this a little bit in my other videos numerously, and this is not my PowerPoint, so I don't want to like excessively use it. And I think all MCAT books do a pretty good job of describing how proteins structures are. Let me just zoom in real quick. My zoom is really small on this, so it doesn't work. Okay, so you already know this. Primary structure of amino acids, just the sequence. So it's just like if you have a sequence of like, can you guys hear me? It says my internet's being unstable. Okay, good. Let me know if you guys can't hear me, because sometimes like this time of day it like just goes off. Okay, so let me know. The primary structure is generally when you have like the sequence, it's just like what the code is. So you in a protein. So it's like this protein is made out of a leucine, a valine, an arginine, a proline, alanine, a glycine, a do you guys remember what N is off the top of your head? Is it too early to test you guys? Okay, all right. Yay, good job. Asparagine, yes, and this is asparagine. So in a sense, for primary structure, it's just what makes up what amino acids make up the protein. It's not that hard. It's the general sequence, primary sequence. So I'm not going to get into more details on that. Secondary structure is a little more complicated. It's basically the hydrogen bonds between the C double bond O and the NH group in an amino acid between the backbone of amino acids. So you have like this group and the amino acid generally, right? and then CO. Wait, what am I doing? For example, and then there might be in another amino acid, right? And then blah, 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 it moves on, blah, blah, blah. And then there'll be another amino acid, like right here. And then these two will have a bond. That's generally how a hydrogen bond works. And with the secondary structures case, it's between the backbone of the protein, which is different than the tertiary structure. So because you can find hydrogen bonds in a tertiary structure or a secondary structure, but the main difference is that the secondary structure is made up of hydrogen bonds, and it is between the backbone. And it's made up of alpha. It can be made into an alpha structure, secondary structure, or beta secondary structure. It's anti-parallel with, oh my god, I spelled that wrong. For alpha, it's anti-parallel. For beta, it's parallel, I believe, from the top of my head. I could be wrong. Let me double check in the PowerPoint. Beta sheets, right-handed, is the alpha helix. Yep, it's not that complicated. These aren't mine, so I'm not gonna go over that. Just know that beta sheets can appear parallel or anti-parallel. They just are more often the case is parallel from what I've seen. They're stabilized by the same bonds. You find proline kind of involved in beta sheets, but they make them more rigid. What else is there? Okay, tertiary structure is a little bit different in this from primary structure, meaning that it's not between a disulfide bond is an example of a tertiary structure. It's between the side chains. So you have an amino acid, and the side chain is a sulfur and amino acid, which is cysteine. Probably this is like a disulfide bond. That's an example. Another example is you have so you have amino acid. You have a COO minus, right? And then you have another amino acid and the NH3. And this will give like a proton, so there's a bond right there. This will be a hydrogen bond, right? Or not hydrogen bond. And then another example would be an amino acid that has a COOH, right? And then you have another amino acid that has an NH3. And the hydrogen bond would be between this and this. That'd be another that'd be another example of a tertiary structure. So tertiary structure is bonds between the side chains. It can be disulfide bonds, hydrogen bonds, electric bonds, or electrostatic bonds, I think that's called. Metal ionic bonds, like just as long as there are structures between the side chains, that is a tertiary structure. Fibrous protein, like stuff you generally know. Folding, yeah, hydrophobic interactions is another example of this. Hydrophobic, electrostatic, ionic hydrogen bonds. Don't confuse them with the secondary structure. That's really important. No, that's not how to do it. And remember, disulfide bonds are covalent, meaning they're strong. And when going through SDS page, gel electrophoresis, you need to go through reducing conditions in order to fully break them, because it's a reducing reaction, reverse them to turn these sulfur groups, the sulfur bond, back into two cysteines. You don't really need to know that. And I mean, like, no, I don't really know many groups that really discuss it, but coordinate structure of proteins relates to the interactions between separate polypeptides chains within the protein. Just a main example of this be hemoglobin. I don't really see many questions discussing, but you just need to know what it is. So hemoglobin is a main example of this. Remember, hemoglobin is that thing in the red blood cells that takes in the oxygen depending on when you want it and when you don't want it. And protein folding has protein folding has a lot to do with its function. So you can denature a protein, or rather remove its functionality by denaturing it. And the reason why in SDS page you want to denature it is because you want it to be in its linear format so that it can be moved based on its size, because you put a negative charge on it by putting in the SDS anions on it. So in SDS page, you want to denature the protein to make it non-functional so it doesn't react with the polymer that is making sure that that is being used in the machine or in the gel. So it all has reasons for this. So, and when you denature it, so you can denature it by using like a strong reagent. So you'll have like this is the protein. It might be folded like this. And then you make it go through extreme heat. Or you put urea or something else. And then you make it go through this, make it a long sequence. So you basically get rid of its special three-dimensional format. Okay, so that's all I have for this subject. Do you guys have any questions? No, you guys have any questions? Oh, no problem. I hope it helped.